I have found that the various discussion classes yesterday made significant differences in degrees of progress. So to try to be sure that everybody gets the same stuff, we'll retreat to the point of least extent or degree of progress reported to me by the discussion class gatherings. From the data at the end of Chapter 20, Table 1, Thermodynamic Properties Data Table, you found that. With that information, you can calculate Ka values for strong acids. Nitric acid, sulfuric acid, perchloric acid if you wanted to, and hydrochloric acid, given that those are the only acids listed in our acid-base table stronger than hydronium ion. There are other stronger acids than hydronium ion, but we are just referring to the ones which we have so far previously considered, although we haven't done anything with perchloric acid. If the listing is correct in our acid-base table, we'll recognize that Ka perchloric will be the largest value and Ka nitric will be the smallest value relative to 55.5, which is Ka hydronium ion. Now we all got through the Ka stuff for nitric and sulfuric. Ka sulfuric on the order of 10 to the 11th, that's a big number. Nitric 10 to the 4th, which keeps with their order of strength listing in our acid-base table. Now KaHCl, some of you looked at this yesterday, some of you did not. Here's the ionization reaction. We're quite familiar with this. From Table 1, you extract the standard free energy formation for the component species. And as we've already mentioned, you needn't include delta G sub F super 0 for water and hydronium ion because their delta G sub F super 0 values are identical. So those values are not part of computation of delta G0 for this reaction. Here's delta G0. We set that equal to minus 2.3 RT log K because we want to get K. You get K of 2.0 times 10 to the 6th. Big number. And in keeping with the listing, strength listing in our acid-base table. Bigger than K for nitric, smaller than K for sulfuric. Now, what does this K equal unit-wise? Moles per liter, molar concentrations, divided by partial pressure. Because under normal laboratory conditions, and the data in Table 1 is tabulated for normal laboratory conditions, HCl is a gas. So you'll have M capital for molar concentration squared divided by atmospheres. Can't do anything from a calculation standpoint with these units not agreeing with each other. So what we wish to do to make more sense of this expression is to turn partial pressure for HCl into its corresponding molar concentration. In other words, we're simply going to believe that the HCl will dissolve completely in the water, which it will. And convert that to this by applying PV equals nRT, treating HCl as a gas whose behavior is functioning ideally. Good enough at 25 centigrade.
Where did you get the 0.041?
Well, just a minute. Just a minute. Okay. Now then, what are we going to do to calculate this? What numbers are you going to put in to calculate this? What are we going to put in?
1 atmosphere.
Standard conditions, right? We're considering this at standard state conditions and trying to answer the question, if this system is constructed at standard state conditions, what will it do? Partial pressure 1 atmosphere for HCl gas. R, 0.0821 liter atmospheres per K mole. T, 298 K. That's equal to N over V. What's N over V? It's molar concentration. This gives us 0.041, so that tells you how to get this. You can put it in numbers. All right? So, we've succeeded in converting this expression to this expression. So now that everything is in moles per liter. If we apply this, we can at a glance see that the resultant molarity of HCl will be, practically speaking, how much? 0. Just like for nitric, just like for sulfuric. Keeping with the fact that they're strong acids. And do you see that the top term maxes out at 1.041? If this is what you're starting with, and all of this becomes hydronium ion and chloride ion, then this is 1.041. End of story. Okay?
Where did you get 1 from?
1 what?
How do you add 1 plus?
We're starting at standard state conditions. Standard state conditions means everything's in the system in the standard state. Partial pressure 1 atmosphere. Molarity? What is it? 0.00000. Molarity? Standard state? 1.000. Okay? That's what we got here. In the standard state, initially, these are each 1 molar. Right? And now we found out what standard state partial pressure for HCl corresponds to concentration-wise. We okay on this part? Good. So, practically speaking, this tells us that the equilibrium molarities of hydronium ion and chloride ion will be on the order of 1.0. 1.041. Where this becomes effectively 0. All right? Well, we can put all this information back into this. Because now we know these concentrations after the reaction has taken place. So we can calculate the partial pressure of HCl using this relationship after the reaction has taken place. And we get this marvelous, whoops, oh, here it is. Equilibrium partial pressure of HCl of 5.4 times 10 to minus 7 atmospheres. And again, if you operated on this arithmetic, you'd get 2.2 times 10 to minus 8 molar. Think it's fair to say that all the HCl went away? Yeah, that's pretty fair to say all the HCl went away. Okay. You work through the arithmetic. 21.2. 21.2 corresponds to a question which chemists today are still wrestling with. In my opinion, why? I don't know. But theoretical chemists are still wrestling with this issue. The issue being, since H plus has an extreme positive charge density, it's only +1, but it's a bare nucleus. So +1 charge smeared on the surface of a bare nucleus corresponds to one hell of a charge density. So why should we believe that H plus interacts with only one water molecule to become the hydronium ion? Put another way, some theoretical chemists who deal with this have speculated that H plus associates with 2 water molecules. So you get H5O2 plus. Or 3 water molecules. And you get H7O3 plus. Or 4 water molecules, you get H9O4 plus. Who cares? To me, I find these speculations to be not keeping with fundamental chemistry. On what basis? To form hydronium ion, H plus behaves as a Lewis acid, and water molecule behaves as a Lewis base. Remember this at the end of chapter 19? What's a Lewis acid? A species which in its valence environment has one or more empty valence orbitals. How many empty valence orbitals does H plus have? 1. Well then, how many coordinate covalent bonds can it form? 1. Hydronium ion, enough said. H3O plus. Because once one water molecule interacts with H plus, I have filled this one empty valence orbital and made the maximum number of coordinate covalent bonds which an H plus can form, unlike aluminum ion, which can make 9 coordinate covalent bonds, for example. Period. How about Li plus? Li plus derived from lithium in family, in period number 2. Beryllium, 2 plus. How many coordinate covalent bonds can those ions form? 4. Because they have 2s and 2p valence orbitals. NBE2 plus, for example, has no valence electrons. So all its valence orbitals are there and empty. 21.3. 21.3 is just a little bit more arithmetic and seeing how well you understand these calculation aspects of thermodynamic information. How well you can grapple with such. We talked about getting this stuff, teacher's favorite weapon, to decompose spontaneously under standard state conditions. Well, under standard state conditions, the partial pressure of CO2 is 1 atmosphere. So, since at 1 atmosphere, partial pressure of CO2, the equilibrium constant for the decomposition is 1. And the log of 1 is 0, which means delta G0 is 0. If this reaction is at equilibrium under standard state conditions. And for that, we calculated a temperature by setting delta H0 equal to T delta S0 of 1091 Kelvin. My memory's right. And said that if you now take this calcium carbonate stuff and heat it to a temperature above 1091, it will continue to decompose spontaneously if you run this decomposition in an open atmosphere environment where the partial pressure, where the total pressure of the atmosphere acting on the calcium carbonate is 1 atmosphere. Because at a temperature above 1091 K, the partial pressure of CO2 produced by this decomposition is greater than 1 atmosphere, and it'll push the air atmosphere back because you're not operating in a closed system. But in this system called air, what do you think the partial pressure of CO2 actually is? If we wanted to get this stuff to decompose spontaneously by heating it, you think we'd have to heat it up to 1091 K? Why not? Is the partial pressure of CO2 in this air atmosphere 1 atmosphere? Hell no. If there was nothing but CO2 in here, we wouldn't be able to breathe. Right? Remember what I told you the first day? Part of what I do has to be acting. It has to be. I've got to command your attention. And the best way to do that is by entertaining you, keeping you interested. If I just stand up here and scream and cuss and growl, pretty soon people say, no good bastard, we go away. Okay? Now then, I'm sure the partial pressure of CO2 in this room is a lot less than 1 times 10 to minus 3 atmospheres. That's probably about something like 1 times 10 to minus 5 atmospheres. I don't know. But I picked this number out of a hat. Who cares? But if you can do it at 1 times 10 to the minus 3 atmospheres, that is to say, recognize under what temperature condition this reaction will be spontaneous, and you can do it at any partial pressure condition for CO2. Because we know that the change in standard free energy for the reaction is a change in standard enthalpy minus T times the change in standard entropy, pardon me. And that's equal to minus 2.3 RT log K. But now, we're not operating with this system at a partial pressure 1 atmosphere. Now we're operating at a partial pressure 1.0 times 10 to the minus 3 atmospheres. So what's the log of K? I got it on the board. It's minus 3. Did you not recognize when we talked about pH arithmetic and the like, in case you didn't get this in high school math, that logs are exponents? Did you get that? Well then. So, when we're operating in base 10, log to the base 10 is the exponent on 10. Minus 3. Okay? Done. So, you put in the data points which we already determined for delta H 0 and delta S 0, and we want to know the temperature. So you rewrite this relationship. You got one unknown, it's T. Calculate 806 Kelvin, which of course is much lower than 1091 Kelvin, as it must be. Because the higher the partial pressure of CO2, the higher the temperature we have to raise this system to in order to make the system continue to go, for this reaction to continue to go. And that's enough on chapter 21. So now we go to chapter 22, which again, a number of you have already got a start on, and that's to your benefit. So for you folks, this will be, at least initially, review. Electrochemistry. Qual for qualitative and quant for quantitative. Study of redox reactions. And I trust by now you've recognized we always start with the qualitative stuff first. Let's develop some ideas of what this stuff is about before we immerse ourselves into the arithmetic part. Because if we start with the arithmetic part, you're going to be doing calculations on a bunch of stuff you don't understand, which to me is totally without point. Redox reactions. Did you talk at all about redox reactions in Chemistry 2045? Were you asked to consider at all redox reactions in Chemistry 2045 laboratory? You're damn right you were. Remember that investigation? Assignment 5, Part 1. Wasn't anything fancy, but it was intended to show you the very fundamental considerations upon which redox reactions rest. In a redox reaction, one of the reacting components behaves as the reducer. The reducer is the stuff which gets oxidized. Because from an electron give and take standpoint, the reducer, think of what the word means. I am the reducer. I'm going to do something to make your charge get less plus or more minus. So am I going to give you electrons or take electrons away from you? I'm going to give electrons to you. That's the way I make your charge go down in chemistry. The other stuff's the oxidizer. So if I give electrons to you, you are functioning as the oxidizer. You are taking the electrons from me as the other reacting partner in this system. Now what do we convert to? I as the reducer, you as the oxidizer. I convert to the oxidation product. You convert to the reduction product, the stuff made by reduction. I convert to the oxidation product, the stuff made by oxidation. Nothing fancy about that. The example discussed in the notes is sodium reacting with chlorine. Equation for such, without fractional coefficients, would be this. Another redox reaction we've looked at. Liquid or gas. Remember the boom bottle? Had fun, shook it up, nothing happened. Open the top, put the contents of the bottle next to the lit burner, and wham! Everybody said, whoo! But just to prove that you weren't scared, I asked if you wanted me to run that reaction again. Everybody said, oh yeah, we like that. Fireworks. Now, a way by which, or I should say the way by which, for a redox reaction, you can recognize what stuff is the reducer and what stuff is the oxidizer, is to pay attention to atomic numbers, atomic oxidation numbers for the component atoms of the reactants, and compare such to atomic oxidation numbers for the component atoms of the products. You did this oxidation number stuff, at least to some extent in 2045, because oxidation numbers are very much a part of chemical nomenclature. Like iron 2 chloride versus iron 3 chloride. Nitrogen 1 oxide versus nitrogen 2 oxide, stuff like that. Did you learn that the oxidation numbers for atoms of elements, oxidation numbers for atoms of elements is always what? Zero. Lewis structure for a water molecule. To find out then if hydrogen is the reducer or oxidizer, same question applied to oxygen. Since we know the oxidation numbers of the component atoms of the elements, 0 for these reactants, we write the Lewis structure for the water molecule. And then follow the best path available to get at oxidation numbers for component atoms of species. And that's by writing Lewis structures. Unfortunately then, when you were introduced to oxidation number assignments and considerations regarding such in 2045, you did this at the start of the course. You hadn't yet talked about Lewis structure, so you couldn't follow the Lewis structure route. But now you can. And now you will. So again, some of you did this yesterday in discussion class. Here's the water molecule, for which I have written the Lewis structure. Bearing in mind again that only on rare occasion do I use dots for non-bonding electrons, because to me that's too messy in my chalk storm up here. After we have the Lewis structure, you go to each bond site. Each bond site, and you parcel the electrons. How do we parcel the electrons? We give them entirely at each bond site. All the electrons at each bond site. We give all the electrons at each bond site entirely to the atom of greater electronegativity. So this will obligate you to remember stuff that you learned about electronegativity in Chemistry 2045. I told you this before, I'll tell you again. Was it a lot of fun to learn about electronegativity?
I
FON, fluorine, oxygen, nitrogen. FON, fluorine, oxygen, nitrogen. Now, chlorine has an electronegativity the same as that of nitrogen. In some tables, it's cited as being even a little bit larger. But there are a heck of a lot more important molecules with nitrogen in composition, like amino acids and proteins and such, relative to important molecules which contain chlorine. So I like the device FON, especially because these three atoms are neighboring atoms in period number 2, and by now you should have learned enough chemistry to realize when you start thinking about all the molecules contained in the world, what do you find to be the most common atomic components of all the known molecules? Number 1 is hydrogen. Number 2 is carbon. Number 3, oxygen. 4, nitrogen. Goody! So I like remembering stuff that relates directly to the chemistry of most all known molecules. And you should have also learned, I think, in Chemistry 2045, that if we take the electronegativity value of fluorine to be 4.0, which is what it's cited as in most tables, like the Pauling electronegativity scale. And remember that for neighboring atoms in period 2, between neighboring atoms there's an electronegativity difference of how much? 0.5. You can run down these atoms from right to left for period number 2. Fluorine 4.0, oxygen 3.5, nitrogen 3.0, carbon 2.5, on. And the only other atom whose electronegativity, I argue, it's worthwhile to remember, is that of hydrogen. We just said why. It's the most common atomic component of all known material. What's the electronegativity of hydrogen on the Pauling scale? 2.1. That's it. So here we go. Oxygen, considerably more electronegative than hydrogen. So there's the parceling. And after we parcel, we apply a rule then to calculate oxidation number. What's the rule? It's in the notes. You take the number of valence electrons which the atom has all by itself. That follows from the periodic table. Notice that this game only applies to A family atoms, because transition metals have a variation in number of valence electrons depending upon the chemical environment in which they are considered. How many valence electrons for an isolated oxygen atom? 6. How many valence electrons does oxygen have after we played this parceling game? 2, 4, 6, 8. 6 minus 8? Minus 2. There's our oxidation number for oxygen. Hydrogen all by itself, 1, 0. 1 minus 0 equals plus 1. There's the oxidation number for each component hydrogen atom of the water molecule. Now keep in mind, oxidation numbers do relate to chemistry, but they are not charges. To say that in the water molecule, hydrogen bears a charge of plus 1 and oxygen bears a charge of minus 2 is dead wrong. It's not an ionic compound. Component atoms don't have charges. It's not like sodium chloride, which is ionic, where sodium in sodium chloride is formally plus 1. And the chlorine atoms in sodium chloride are formally minus 1, more commonly called chloride ions. But this answers the question. What's the reducer? The reducer is the stuff which gets oxidized, because the reducer gives electrons to the other stuff, and in so doing gets oxidized. Hydrogen 0, hydrogen plus 1, there's your reducer. Oxygen 0, oxygen minus 2, there's your oxidizer. This thing got the electrons and became converted to an oxidation state is lower than what it started with. 0, minus 2. What's the oxidation product? Water. What's the reduction product? Water. Because water contains the atom that got oxidized as well as the atom that got reduced. Now then, what you did yesterday in discussion class is to go further with this parceling business, for those of you who got this far. You looked at nitrate ion, and by analyzing nitrate ion, just like we analyzed the water molecule, you'll get +5 as the oxidation state for nitrogen as the central atom in the nitrate ion, and oxygen -2. Not surprising, because oxygen is -2 oxidation state-wise in just about all oxygen-containing materials. Exceptions, peroxide, where oxygen is -1. Superoxides, where oxygen is -0.5. Shows you again that oxidation numbers are imaginary numbers. And this stuff, oxygen difluoride, which is the only known material, to my knowledge, in which oxygen bears a positive oxidation state. Not surprising, because in this material, oxygen is chemically bound to the most electronegative atom, fluorine. Now then, along with nitrate ion, I asked the folks yesterday to take a look at acetic acid. I'll repeat that analysis. To give you a chance to play this game successfully, I'll write the formula for acetic acid like this. Because for a type formula, this is about as good as I can do as I type a formula, in this case to correspond to the structure of acetic acid. But sometimes even the best type formula will lie to you. How does this formula lie to you? There are no oxygen to oxygen bonds in this molecule. So if I were to ask you this or something like this on an exam or quiz, I would tell you. Recognize that even though this is the type formula, there are no oxygen to oxygen bonds. Here's an sp3 carbon, tetrahedral geometry with respect to this carbon atom. Here's an sp2 carbon, trigonal planar geometry with respect to this carbon atom. You think the bond angles here, here, here for this trigonal planar carbon, you think these bond angles are perfectly 120 degrees? No. Which bond angle do you think is larger? Is it this? Is it this? Is it this? I'll let you ponder on that one, because we're going forward with the oxidation number stuff. After we have this Lewis structure written, we play the game of parceling electrons at each bond site in favor of the atom of greater electronegativity. So, carbon 2.5, which beats hydrogen at 2.1. Oxygen at 3.5, which beats carbon at 2.5. We already recognize that oxygen certainly beats hydrogen from an electronegativity value standpoint. And when we get to a bond between like atoms, since the like atoms are obviously of identical electronegativities, how do we parcel the electrons at a bond site between like atoms? Divide them in 2. So I'll do that. All right? So with this, let us write down the oxidation number for each component carbon atom. Carbon by itself, how many valence electrons? 4. Less. 2, 4, 6, 7. Minus 3 for this carbon. This carbon. 4 less 0, 0, and 1. Plus 3. Now, how might we show the correspondence of these oxidation numbers to chemistry of the acetic acid molecule? Well, number one, I have seen general chemistry textbooks and teachers who will take the acetic acid molecule and choose to report an average oxidation number for carbon. That's 0. And that's stupid, because it doesn't keep with chemistry. Damn it, this is chemistry class. I get mad as hell when I see chemistry classes dodging chemistry. What's going on here? I'm going to write 2 words on the board. How many of you heard these words yesterday? Nucleophile, electrophile. You remember the Lewis acid, Lewis base language? Is an electrophile a Lewis acid or Lewis base? One or the other. Electrophile. What does the word mean? Translate it.
You love electrons.
That's right. Electron loving versus nucleus loving. What kind of charge do electrons have? Negative. Minus. What kind of charge do nuclei have? Plus. Is the Lewis acid the electrophile or the Lewis base the electrophile? Which is the electrophile? What does a Lewis base do? It supplies an electron pair. Damn it, if I got an electron pair to supply, I'm looking for something that's plus. Right? Because the plus attracts my electron pair. So the nucleophile is the Lewis base. And the electrophile is the thing that wants these electrons. So it's looking for a Lewis base, right? And regarding this language, this is the thing with the empty valence orbital. Electrophile. It's looking for electrons to get into its valence environment. Nucleophile. This is the thing with the electrons to give. It's looking for something that attracts these electrons. It's like a nucleus. You won't find anything that attracts electrons better than a nucleus. So, how does this relate to chemistry? See these oxidation states we've determined for the relative carbon atoms? If this stuff reacts with an electrophile, do you think the electrophile will tend to attack this carbon or this carbon? Which carbon will be preferentially attacked by an electrophile? Which carbon will be preferentially attacked by a nucleophile? The electrophile. Looking for electrons. This is a -3 carbon. This is a +3 carbon. The electron density of this carbon is considerably greater than the electron density of this carbon, because this carbon is in an environment where electrons are withdrawn from its nucleus, from its valence environment, pardon me, because of oxygen, right? So the electrophile is going to look at which carbon to react with. This one. Right? This is the -3 carbon. The electrophile says, ha-ha, this carbon is richer in electron density, I'm going there. And the nucleophile is going here. See how the game plays? Now then, just to be sure you're understanding this game, let me give you one to operate on. On the board, I'm going to write the Lewis structure for an important amino acid. Its name is histidine. One of the questions in the notes asked you this. But rather than bother with having you search for the Lewis structure for histidine, which is easy to find, I'll give you that. Histidine has in its structure this 1, 2, 3, 4, 5 atom membered ring. And remember, it is an amino acid. You'll learn in organic class that when you see this C double bond, C single bond OH, you're looking at a carboxylic acid, an organic molecule which is a Bronsted acid. Oops. Left out an atom. There we have it. Now, one very interesting chemical feature of amino acids, as we've got this on the board, is that amino acids have the interesting chemical capability to react with itself. An amino acid can react with itself and form what is known as a Zwieter ion. You can look up Zwieter ion, Z-W-I-T-T-E-R ion, on the web or dictionary, whatever have you. How might you imagine this to be able to react with itself? Tell me. For this picture that I've drawn, do you see that this thing not only can behave as an acid by losing this H as H+, just like acetic acid, that this thing can also behave as a base? How might you expect this to behave as a base? You see this NH2 group? See this? How about that? Behave as a base. How about this one? Well, you think about this nitrogen. We'll talk about this chemistry later in chapter 23. But here's the Lewis structure for histidine. You parcel electrons and find out the great variation in oxidation number shown by the carbon atoms, of which there are 1, 2, 3, 4, 5, 6, and only 2 of these carbon atoms have the same oxidation state. See if you can figure out which 2. It's pretty easy if you parcel electrons properly. All right, we'll pick it up from this point next time.